Hello, everyone. Our team is going to present the topic of data analysis on New York City motor vehicle crash injury prediction. Vehicle crashes occurs thousands of times a year, especially in New York City. There were 243 fatalities in 2020, which is the deadliest year for motor vehicle accidents in NYC in more than 50 years. Our motivation is that motor vehicle crash is a severe problem killing hundreds of people. We want to perform prediction analysis to help the government optimize the medical and police resources distribution. The impact of our project will be allocate the medical and police resources to reduce fatality rate by building a statistical model to predict if there will be injured person in a specific motor vehicle accident in a certain area. The data we used is NYC vehicle crashes data from the past 10 years, from July 1st, 2012 to today. There are in total of 1.8 million rows and 29 columns. The independent variables are crash date, time, borough, location, number of person injured, vehicle type, etc. The dependent variable is if there are person injured.
To get the dependent and independent data, we instead of using how many people are actually getting hurt, we use the binary variable if are people getting hurt in an accident. There are some vehicle-related variables for independent. We created a new variable called vehicle count. Instead of having to analyze every causes for every single vehicle, we just have the primary cause. And we also only select the vehicle types that only occur over 10,000 times. And there's some locational variables that we dropped the latitude, longitude, zip code variables. Instead, according to street name, we counted each street's accident frequency. Then we created 3 binary variables indicating whether the accident frequency in the street is high, medium, or low, based on a detailed histogram. And we also utilized a binary variable on crash time. So we classify crash time into if it's rush hour or not. We drop the dates, and one important aspect of our cleaning technique is that we utilize resampling technique to balance the data, since we have a distribution of true or false close to 4:1, which results in a very high baseline model. The team decides to perform model prediction based on both original data and the resampling data. And the summarized results are shown at the very end. This is the baseline model on the resampling data. We have a baseline approximately to 50%.
So for the logistic regression, we split the data into test and training set, and then we feed the model and make the prediction. The confusion matrix and performance evaluation are as follows.
And this is the cart. We run the cart model with the cross validation. We adopt CCP alpha equals to 0.0111. And we did use the classification tree model. For
boosting model, we ran with an estimator of 1,000 and max leaf nodes of 10, and we got a 0.63 accuracy and high TPR.
For the backend model, we are using all features to build trees for the random forest classifier, and the performance evaluation is shown below.
For the random forest classification, since the data is too big to be processed using research to find the best M features, so I stayed with the default setting, and my accuracy for the resample data is about 62.5%.
And as we talked about earlier, this is the result of original data. We have the original baseline model close to 80%, and it's not a huge improvement, and it results in very low TPR, FPR. And but this is the result of resampling data. At very last, based on 2 models, we decide to adopt the boosting model, since it does have the highest accuracy and very high TP true positive rate with acceptable false positive rate. Thank you very much for listening. That'll be all.